All right, so exam 1, number 2, you have an object suspended from a cable in this direction, and you're given that it makes an angle of 30 degrees with the vertical. So let's say that this is 30 degrees. Well, that cable force is going to act away from the body. So this is the direction of the vector we want. A lot of people had that facing the other direction. And so to come up with the angle that we need, here's the coordinate system. Now the first vector I'm going to draw is the one that angle is shown for. And all of the vectors I'm going to draw have their tails at the origin. So I'm going to draw one like this, where this angle is 30 degrees. But that's not the vector we want. We want the opposite one. Okay, so this is this angle is -60. Okay. The vector we want though is this. And it's 180 either direction to get from this -60 to that one. So if you start out at the positive x-axis, so clockwise 60 and you're here, counterclockwise 180 and you're there. -60 plus 180 is 120. And we're saying that the tension is T. So this vector, this force vector, is T times the cosine of 120, T times the sine of 120. And so that's -0.5 T, positive 0.866 T. Any questions about that? Okay, and then anybody want to see number 3? Anyone want to see number 1? Well, let me just say about number 1. So you take the cross product of those two in either order, and then that vector you get is perpendicular to both of those. And if you multiply it by -1, that's the other one that's perpendicular to that. A lot of people forgot to make it a unit vector. So if you take the cross product, you get a perpendicular vector, but it's not a unit vector. I think a bunch of people did it. I figured it probably wasn't based on a misunderstanding, really. So I took off 1 point for that. It was probably a little generous, but yeah. So remember that you have to divide. So once you get those two vectors, you have to divide by the magnitude of the vector to get unit vectors that are perpendicular. Okay. Anyone want to see 3? Not really. Okay. So 4. What? Oh yeah, 4. That was a big one. So what we're trying to do, so we have this vector u, and it is xy, xz, and y cosine of z. And we have to assume that these variables are changing in time. Okay, that's what there's no reason to believe those are constants. So x is equal to x of t, y is equal to y of t, z is equal to z of t, and we want to calculate u dot. So this is just an exercise in product rule and chain rule. So first I'm going to use the product rule, and then there'll be one case where I have to use the chain rule. So U dot is equal to, the product rule says for the x component, that's x dot y plus x y dot. For the y component, that's x dot z plus x z dot. And for the z component, that's y dot cosine z plus y times, let me write it like this, cosine of z dot. Okay, that's what the product rule says. But now we have to figure out what this cosine of z dot is. Everything else is in the, because you were only given 6 things that could appear in the final answer, and cosine of z all dotted is not one of them. So now let's go into cosine of z dot. Well, cosine of z dotted is, this is, d dt of cosine of z. And the chain rule says that's d dz of cosine of z times dz dt. Okay, that's the chain rule. And so d dz of cosine z is negative sine z. And then dz dt is what we're representing as z dot. So now substitute that in, and you get u dot is equal to x dot y plus x y dot. For the y component, x dot z plus x z dot. And then for the z component, y dot cosine of z minus y z dot sine of z. So this is all product rule. And this is all chain rule. Come on. Any questions about that one? And then 5 is short, so I might as well do that. This was the chain rule thing. So we know that the velocity is equal to negative 10y, negative y squared. Okay, this is the velocity as a function of y, where the position vector is x, y. And so the acceleration, the definition of acceleration is dv dt. That's never wrong. And we can write that using the chain rule. So that's dv dy times dy dt. dv dy is negative 10, negative 2y. dy dt is the y component of the velocity, so that's negative y squared. And so you get 10y squared positive and positive 2y cubed. Yep.
Just one question regarding the notation. When you introduce that bar dot,
yeah,
that is with derivative with respect to time, but that is also like an x prime of t as well, right? Like there's the same notation or different notations for the same thing.
Yeah, so if I have anything I write is like
I hate Leibniz notation. I'd rather use primes if I can help it.
oh, well, for time you should always use the dot. Okay. So and I don't know if that's Leibniz, it's sort of the same thing, but the dot always means time. Prime is like a general thing. It's just like whatever your variable is, use that. But dot always means time. Okay.
So just with respect to t then.
Yeah. So this always means ddt of x cosine y. That's the only thing that can mean. Okay. Oh, okay, Leibniz, that's the DDT. Oh, okay. Yeah, I got it mixed up. So, okay, well, the dot is the equivalent of the prime, but for time. Yep. And every class you will ever see in your life, any equation you ever see in your life with a dot, that means time. And there aren't too many notations like that. People use all these funky notations, but that's the one thing you can count on. Any other questions about the test? Okay. Okay, so homework questions. So before I get into specific homework questions, you were saying that you were confused because there's all these different types of acceleration. Okay. Okay. There's one type of acceleration. And that is the acceleration that's equal to the time derivative of the velocity. Okay, that's always the definition, and that's always what acceleration is. There's also angular acceleration. But that's just trying to take advantage of the popularity of acceleration. It's just trying to piggyback for, for more Twitter followers and stuff. There's different ways to calculate it. There's a few different ways to calculate it, but this is always what it is. So there's also angular acceleration, that's alpha, and that is always ddt of the angular velocity. I mean, really, like the main reason they have the similar names, angular acceleration and angular velocity, is because there's so many analogous properties between the two. The relationship between acceleration and velocity is the same as between angular acceleration and angular velocity. The rotational version of Newton's second law looks the same as Newton's second law. You just use moments and angular acceleration and stuff instead of force and acceleration. So in a way, the similar naming is just a way to remind you that you can store a lot of the angular information in the same memory spot in your brain as the translational stuff. It's not the same, no. They mean totally different things, you know. Angular acceleration is, so acceleration, A, is telling you, I mean, it's looking at a point and it's measuring its motion over time. It's looking at a point and where does that point go? And if you plot out its position over time, you come up with a function that represents where it is over time, and you take 2 time derivatives. That's the acceleration. The angular acceleration is saying, now it's not talking about a point moving around. It's talking about an object with dimensions changing orientation. Okay? It's changing the angle that it's changing where it's looking. Okay, actual acceleration doesn't know anything about orientations of objects. It's just tracking a point around. Okay, angular acceleration is changing orientation, and so the way you do that is you figure out how much that angle is changing over time, and you take time derivatives, and that's the value. So this one describes how a material point moves. This one describes how a rigid body's orientation changes.
Well, then what's the difference between tangential and centripetal acceleration?
So that's a way to break up the acceleration into components. So that's just saying, you know, you can always break up any vector into perpendicular components. And you can decide what the directions, as long as they're perpendicular, you can, that's like just choosing a different coordinate system. You can always change the orientation that those have as long as they're perpendicular. So tangential and centripetal acceleration are saying that if you have something in circular motion, then break up the components of the acceleration into one that's tangent to the circle, one that's toward the center of the circle, and then the total is just the sum of those two. If you chose a coordinate system where that tangential vector I drew was the x axis and the centripetal was the y axis, then this would just be adding up the x and y components of the acceleration vector.
Okay, so when velocity is constant,
Mhm.
then that one that goes toward the center
Is gone. Yep, that's right.
So centripetal by and just means it's around the center
So
versus tangent.
be careful. It sounded like you said centrifugal, and these sound so similar. But what we're dealing with is centripetal, which means toward the center. Okay. Centrifugal is actually sort of a complicated thing that we know the experience of centrifugal acceleration. We feel it when we're accelerating in a circular path. But when we're in a circular path, when we're going in a circular path, like you're taking a tight turn in a car and you feel centrifugal acceleration, remember that you're functioning as the coordinate system. and that coordinate system is accelerating.
Okay.
Okay? So a centrifugal acceleration is only a thing that exists in a rotating coordinate system. Okay? And otherwise accelerating. And we're not dealing with accelerating coordinate systems. We're dealing with inertial coordinate systems. So centripetal is all we know about for now. Yep. Well, no, what it is, okay, so when you're in a car turning left, okay, so let's all be, so you're turning left, and you feel like you're being pulled to the right, okay? That's, you experience centrifugal acceleration, and your seatbelt has to keep you from falling to the right, okay? So you think like turning the car is applying a force to you to the right, okay? But really, to an observer that's looking at you in an inertial coordinate system, just a camera that's fixed in the parking lot, what they see is, in order to maintain that circular path, a force has to be pushing you toward the center of the circle. And that force is the seat belt pushing you towards the center. Okay. Yeah, so centrifugal is what you feel like is a force pushing you to the right only exists to you because you're in an accelerating coordinate system. So we don't want to think about that yet, okay? To us, everything is in an inertial coordinate system. Yep. The R vector for like circular motion calculations, it depends on the problem. It's always a vector from the center of the circular motion to the object. So in this case, so in this problem, this red would be the R vector. In which problem? The one with the carousel? I think it does say somewhere that the kid is all the way on the right side. But if it doesn't say that, then you just have to pick a point. Yeah. If it doesn't say that, then yeah, it can be any point. So actually, never mind. Okay, yes. No. But I'd be happy to talk to you about it. Okay, well, we didn't cover any new material today. That's all right. Okay, right. Yeah. I don't know. This is something everybody wonders about at different times because in everyday life, you hear the word centrifugal, but that's not what we calculate in this class. And it is confusing because they sound so much alike. But that's because centrifugal acceleration is based on your experience of representing an accelerating coordinate system. And we are doing our calculations for now in non-accelerating coordinate systems. There's one counterexample. I mean, we've done the relative motion equations. So if you're moving in a circular path and you have a okay, and so your coordinate system is this, let's say, okay? Well, we know from experience that the seatbelt is applying a force this way, right? So we have this force pushing on us like that, right? The acceleration of the passenger relative to the ground is equal to the acceleration of the passenger relative to the car plus the acceleration of the car relative to the ground. Okay. And the acceleration of the passenger, let's see, both of these are, I don't know, this is going to be a little confusing. Like the acceleration of the passenger relative to the ground. If you fixed coordinate system is measuring the passenger. They see the passenger going in a circle, and this force is required to go that way. The acceleration of the passenger relative to the car. Well, the passenger, the seatbelt's holding the person into the car, so this is going to be 0. Car relative to the ground, that's also measured by the parking lot camera, so that's going to be this way. Okay. And so the passenger feels no acceleration, or feels is the wrong word, observes no acceleration. But can feel that force is required not to fly the other way. Okay, and so that's the centrifugal acceleration. You're like, man, my body's trying to accelerate to the right. It has to do with the fact that in the person's accelerating coordinate system, it doesn't appear like there's any acceleration, relative to that coordinate system, and so there's this mismatch that people give a name to that's used in everyday language. But centripetal is the one if you're thinking about things in a non-accelerating coordinate system. If there's an acceleration toward the center. Okay, that's enough.